So this here, do we know what form this guy is in? Amanda Baxter, you start last. Yes? Yes, vertex form. And vertex form is, does anyone know it? All that's y equals a x minus h squared plus k, where h, the point hk is the vertex. You take this guy, and go ahead and paste it. See if we can graph this. So the vertex of this guy, look at here, we have, what would be the vertex? That's a good starting point for these. Other than 7 and -1, thank you. Alright, 7, -1. So 1, 2, 3, 4, 5, 6, 7, -1. And now that we're here, all we really need to do is set up a table of values. Got this really crazy one here on this y. Okay, now, is there any, if we look at the original vertex form here, actually, no, I'm going to label this as vertex form. If we look at this, what tells us if there's going to be any sort of vertical stretching or compression compared to the parent function? What value tells us that? Is it the A, the H, the K, or some combination? Yes. It is the A, thank you. So this guy here, right here, he tells us if there is any vertical, this screen's awful on the eyes. I don't know about you guys. Let's go here. Let's go. It's easier to see. This is the vertical stretching or vertical compression. Okay, so let's review. When does the graph look stretched compared to the parent function? Remember what value of A needs to be so that it looks like it's no longer just going to be the original looking parabola, but it's going to look stretched. Do we remember? What's that? If A is greater than 0, we know that it's going to be concave up. We do know that. But for stretch and compression, all we're really concerned about is the absolute value of A and whether that is fractional or greater than 1. If you think about it, if it's fractional, it's like, okay, for example, A were 1/4, it would only go out 1/4 compared to the parent function, as high as 1/4. But if we're something, let's say A equals 5 or -5, that's going to be stretched by a factor of 5. It's going to have an output of 5 times the amount, whether it be negative or positive. The negative or positive is just the reflection in the x-axis. So for here, the A, again, and this is just started being your notes, but the absolute value of A, so if the absolute value of A is greater than 1, that is a vertical stretch. And they'll say something like vertical stretch by a factor of A, or absolute value of A. And then if the absolute value of A is between 0 and 1, So if 0, if it's, let me say this. In other words, if they were something like -1/4, +1/4, 2/3, 4/5, -4/5, anything where the absolute value of A is fractional, then we have vertical compression. That's pretty awful handwriting, so I'm going to write that word better. Compression. So looking at ours, what is the value of our A? It is 1, thank you. So because it's not written, it's understood to be 1, so there's going to be no stretching or compression. Okay. Now this gives you, again, it gives you a general idea knowing what A and H and K and what it looks like compared to the original parent function. But here's the thing about vertex form. Once you graph the vertex, you can just plot points, and it'll just come about naturally. So what I like to do is I'll plot the vertex at 7, -1. I'll double check. 1, 2, 3, 4, 5, 6, 7. This is definitely 7, -1. That's my vertex. And now I will just simply pick x values to the left and right of this point a couple times, see what their y values are, and then plot those points and graph it and be done with it. So let's go ahead and what would be a value, an x value, just to the left or right of the x value of the vertex? If this vertex is here, this is 7, -1. This point right here. What would be an x value just to the left or right of this vertex? 6, thank you. So 6 would be just to the left. So here's what you can do. You can now just take 6 and throw it in there and see exactly what you get. You don't have to worry so much about, oh, let me go back to the parent function, see when I input 1, I got an output of 1. You can do that, but this may feel more natural to where, okay, if x is 6, let me substitute 6 in x. Let's go ahead and do this. So 6 minus 7, 6 minus 7 is -1, and then what's -1 times itself? +1, and 1 minus 1 is 0. So we have the point 6, 0. 1, 2, 3, 4, 5, 6, 6, 0. Now, knowing that this is going to be a parabola, knowing that it's going to be symmetrical about the axis of symmetry, can't I just go ahead and now plot this point here as well? Because this thing is going to be symmetrical. And again, even if you're not sure, you can go ahead and you can try something. Okay, well, what would that be? That would be 8. That would be the point just to the right of the vertex. Let's see if it in fact does give an output of 0. Let's see, 8 minus 7 is 1, 1 squared is 1, and 1 minus 1 is 0. So yes, in fact, it does give us 8, 0. And like I said, 2 more points, and that would be enough to graph a decent looking graph. So let's keep going with this pattern. So we pick points just even on each side. What's another value? Let's go 5, right? Yeah, 5. And then to the right would be what, 9? And we'll see what we get here. So when we input 5 into this guy, what do we get? 3. I think so, yeah. 5 minus 7, -2. -2 times -2 is +4, and 4 minus 1 is 3. Good. So 5, 3. 1, 2, 3, 4, 5. 1, 2, 3. And then when we input 9, we should also get 3, because it seems to be, well, it doesn't seem to be, it should definitely be 3 because it should be symmetrical. So let's see. 9 minus 7 is 2, 2 squared is 4, and 4 minus 1 is 3. You can also notice algebraically why this is working out is because -2 squared produces the same output as 2 squared. So 9, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3. So there are 5 points. I'm going to go ahead and plot this guy. That'd be a decent enough looking graph for this problem. Obviously, you can't worry about it looking perfect because there's an infinite number of points that make up this function. So 5 is usually pretty good enough. Any questions or concerns about these? So now I said in this warm-up, let's grab the function and state label as much as you can about the function, okay? Yes?
So when you were coming up with the x and y values,
yes.
you were just picking random x values?
Almost random. Just, here's the vertex. So I decided, okay, let me pick some points just to left and right. If x is 7, what's an x value that would be just to the left of 7? 6. Right, I'm going to pick values that are easy. I'm not going to put some weird fractions to plug in. I'm going to plug in some nice whole numbers or integers. So I plugged in 6, and then I plugged in a value just to the right of the vertex, one to the right, which would be 8. Okay. And then I kept that pattern going for 2 more points, 5 points, good enough to graph this thing. Get a good idea on this graph. Good question. So graph the function and state label as much as you can about the function. Okay. So I'm trying to think about everything you know, all the terminology and all the facts that you know about this guy. So that way, when you have on a test, if it asks about all the different things, what can you say if you're just told in general? Good morning. If you're just told in general, do you have a pass? Okay. Really should get a pass from the office. I hate to mark you tardy every single time, but I kind of have to. Let's see. So let's see if we can come up with stuff on our own. Yes?
7 units to the right.
7 units to the right, compared to the parent function. Yeah, so we can discuss things just based on the parent function. Good. So we could say that this function y, so we'll say this function is 7 units. Let me write a little bit thicker than that. Go 1 dot higher. 7 units to the right. And do we remember the name for this particular transformation? Remember the transformations, those are all the guys. Those are all the different things that we can do to make a graph look different. We're describing it related to the parent function. 7 units to the right. What's the word we should use? Let's start with the T. Translation. Good. So 7 units to the right. So we could say it's translated. It's been translated 7 units to the right. And again, this is based on the parent function. So this is described. I'll put. You can say translate 7 units to the right of the parent function. We can say that. The parent function. This word is going to be function. Now remember, I'm abbreviating. I just use F and the underline the end. Just a brief way of writing function. And then looking at this, okay, so we're talking about translations. Are there any other translations? Because what is the parent function, by the way? The parent function is simply, what's the parent function? That's the basic guy. Parent function for quadratic, that's just the simple x squared. F of x equals x squared. So anytime I say parent function, that's the most basic form of this type of function. This is a quadratic function, so the parent function, the most basic would just be f of x equals x squared. All right, so since we're discussing this, we're trying to get as much information, because we've been doing several of these now, as much information as we can about this. Could you tell me if this is in standard form, vertex form, or could you say it's either or? Okay, vertex, you would be correct. Yes? They are both. You can say this is standard or vertex. Okay? I mean, technically vertex, I could write this, right? I could say f of x is equal to x minus 0 squared plus 0. And I could even write a 1 in the front if I wanted. Right? But not really necessary. Not really necessary. There's only one x written. There's only one x written, and it's fully simplified, so you could say this is either vertex or standard. Okay, now that I wrote like this, you can clearly see what is the vertex of this guy. Yes. Yes, you may use your yes. What is the vertex of this guy? 0, 0. Yep, we can see it right here. So I go and I plot this here. 0, 0. And again, same idea here. Okay, I want you guys to know that this table method can be used for any function that you graph, whatever it may be. So let's keep it consistent. Let's keep doing this. So if I let x be 1, what would my output be? If I plug into 1 for x, what would my output? What would f of 1 be? 1. So we have 1, 1. Now we should have, when we plug in -1, because we know it's symmetrical, we should have this. Lillian, if you could, go ahead and join us one of these empty desks. There's one here. Those are like reserved desks in case we need them. And we can go ahead and we can even see that. If I plug in -1, -1 is +1. And then what happens if I plug in 2? Output is 2, or 4, yeah, 4. 2 squared, 2 times 2 is 4. 1, 2, 3, 4. And this should be the same thing over here. If I plug in -2, -2 times itself is also 4. Okay? So I'm doing this just to show when we're talking about translations and so forth compared to a parent function. We can see that now. This guy, and there's this guy. Sorry to draw through the thing here. All right, so we can see, now we already knew there's no stretching or compression because A was 1, but now you can see it graphically. But now you can see translated 7 units to the right of the parent function, and if we were to describe it even further, we could also say that it is translated. What's another translation? That this purple function, or this blue function is compared to our parent function. 1 unit down, and that's you can see that here, and you can see it right here, right? Plus -1 or -1. So translated 1 unit down from the parent function, you could say, from or of. Okay. All right. So we described it that way. What else do you guys know? What else have we learned? What else could you use to describe this? Do we know the axis of symmetry? Do we know this guy? 7, correct. X equals 7, good. So we say this is the x equals 7, and this is called the axis of symmetry. Okay. And we know the vertex, axis of symmetry. Can we describe the concavity of this parabola?
Yeah.
What would we say about the concavity?
Concave up.
Concave up, very good. That's pretty straightforward. If it has the U shape, concave up. If A is negative, concave down. And this we could have seen this very early on before we even graphed it. The fact that our A is positive, concave up. So concave up, I write here because A was greater than 0. Notice I'm not writing absolute value of A. I'm actually just saying A. So if A is positive, concave up. And is there any vertical stretching or compression or any reflections in the x-axis? Vertical stretching, compression? No? Right? Because A, the absolute value of A, right, doesn't fit either one of these. It's not greater than 1. It's not between 0 and 1. It is 1. So because A is 1, there is no vertical stretching or compression. This is because A is equal to 1, or actually the absolute value of A is equal to 1. So that leads us to this point here. Is there anything else we can say? I think that might be it as far as this goes. Stretching, compression, there's no reflection. There's no reflection. I'll say that. There's no reflection compared to the parent function. No reflection in the x-axis. And that goes right along with basically describing concavity. It's the same reason, because A is greater than 0. Here I can actually write A equals 1. Any other questions, concerns about this before we move on? Look at some of the homework. Raise your hand if you have a question about the homework. Yes? Okay. So let's start with homework due page 61. Number 3 and 13, I said yes, you have to graph these two, but as far as 21, 26, and 29, no, you do not have to graph these three. So number 3, 13. I'm going to go ahead and go to 13 because 3 is very similar to this one. It would be graphed very similar. 13 looks slightly different. Says f of x is equal to 0.4 x minus 1 squared. That. What form is this in? This is definitely vertex form. The vertex form again is, say, y equals, you want to have it memorized? A. Very good. Where HK is the vertex. Okay, so let's see what we can say about this guy. What would be the, what's the vertex? This is in vertex form. What is the vertex of our function here? 1, 0. Yeah, 1, 0. All right, so you say, where's the 0? I technically could write plus 0 on the outside here, right? Why is it not 1? Or sorry, why, what was the question? Why is it not 1? Yeah. Well, the x coordinate is 1, because that's the h. This is the h part. And then the k is, remember, that's the constant value that's off to itself, right? In math, we don't have to say plus is 0 when we write something, so we can see that it's 0. If you want, you can technically write plus 0 off the end if you want to see it. Okay? Let's see if we can fit this on the same thing here. Same thing. Okay. Let's go ahead and line. All right, the directions here, they just say graph the function, label the vertex and axis of symmetry. We already have the vertex. Therefore, if we have the vertex, we also have the axis of symmetry before we go on any further. What would that be? 1. Now x equals 1. Very good. Okay, so we already have that. So x equals 1. Go ahead and plot that now. And our vertex is 1, 0. Now it better be, in line with the x, and otherwise I made a mistake. Needs to be. So 1, 0. All right, now we can do the same approach that we did before, where we have a table of coordinates. We can just make them up. All right, okay, what's a point just to the right, just to the left?
1.
All right. So, you know what I'm going to do? Is I'm going to pass this on to you guys and work with your partner and see what you come up with. See, now you don't have to worry so much about knowing what this guy is going to do. When you just plug in values for your x, you're going to see what your outputs for y and just go ahead and graph it. So let's go ahead and try that from this point forward. If you don't have a partner, I suggest that you definitely pair up, unless you strongly prefer to work on your own.